All right, so now what we're going to do is we're going to review all of the double bond, all of the alkene reactions. So real quick, before we jump into this, I'm not going to go over every single step of every mechanism just because that's so much. And honestly, you've seen these before, hopefully, right? This is not the first time you're seeing these reactions. But I am going to highlight a lot of things. So talk about some steps, some intermediates, some stereochemistry stuff, but we're going to run through all of the double bond reactions that we have. We'll start with one of our first ones that we had, which is double bond plus HBr. And notice here, like HBr, HCl, HI, it's really all the same here, some hydrogen halide. Remember, this is a carbocation intermediate. So anytime we have a double bond plus an acid, we'll see this later with H3O plus and H2SO4, we're going to have a carbocation. So carbocation forms on the tertiary position. So this is going to be a Markovnikov addition. So we're going to add the halide, whether it's bromine or chlorine or iodine, to that most substituted position. So let's say that for this problem, we have a bromine here on that tertiary position. Now, in this particular case, we didn't have a chiral center in the end. So that's not a chiral center there. But hypothetically, what if I put a wedged methyl down here in the bottom of the ring? Well, now that carbon where we added the bromine, that is a chiral center. So because of that, whenever we have a carbocation, we can always attack from the top or from the bottom. That's why we get two different options in a lot of cases. Without the methyl here, there's no difference. If you try to find if that's a chiral center, go around the ring, see if you find a difference. There's not. So because it's not a chiral center, we don't draw it on wedges and dashes. But with the methyl there, it becomes a chiral center. So you'd have to consider, what if that bromine is on a wedge? That means the methyl would be on a dash there. And then the other option here would be, what if the bromine came in from the bottom face, so bromine's on a dash, and then the methyl would be on a wedge. And the whole time there, we never touched this carbon at the bottom of the ring. That's why that stays on a wedge. So if you do have chiral centers, then we have to include both. If you're curious, by the way, you're like, what's the relationship with those two things? They're not enantiomers because we have two chiral centers, and these are not mirror images of one another, but they are diastereomers or cis-trans isomers. Technically, both could be correct, but cis-trans is a little bit more specific. Okay, next one, HBr peroxide. So remember, HBr with nothing is just simple Markovnikov addition. HBr with peroxides. And again, there are a lot of different options of these intermediates. Maybe you have like a ditert-butyl peroxide, which is one of the more common peroxides that we can have. Maybe it's just generally ROOR. Maybe it writes peroxides. There's a lot of different ways that we can see this, but this one is the anti-Mark addition. So it's going to add a bromine to the bottom of that double bond, or to the less substituted side of the double bond. So the bromine goes here, and then we add an H to the more substituted side, but we don't draw H's usually, so we don't see the H in the end in most cases, but it is there. So this is an anti-Mark addition. What about stereocenters? What about chiral centers? How many different molecules do I have here? Well, actually, you have turned both of those carbons now into chiral centers. So you actually have 4 different stereoisomers in this product, because when you turn that into a chiral center, the methyl could be on a wedge or a dash. And then when you turn this into a chiral center, that bromine could be on a wedge or a dash. So you actually get 4 different options. There is no sen or anti-pickiness or selectivity. That's why you have all 4 options. You have wedge, 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 dash, 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 and dash wedge. All 4 options there. What about Br2 with some inert solvent like CH2Cl2? And again, this could be Cl2 or I2 above the arrow. So remember, this is our bridged intermediate. I think this is our bridged intermediate, where when we have the bridge, we attack the bridge and we get that anti-addition. So with Br2 and some inert solvent like CH2Cl2 or CCl4, what we get is 1 bromine on one face and 1 bromine on the other face. I always like to draw the halogens first, because then you remember that they're anti to each other. Then that means the methyl that's up here, that must be on a dash. Okay, that's one option. That's if your bridge was up on the wedge when you formed it. The other option is, well, what if you switch those wedges and dashes on the bromines? So what if this bromine here at the top is on a dash, and this bromine at the bottom is on a wedge? That's the other option. Those are both anti still, and then in that case, the methyl would be on a wedge. Now, are those the same thing just flipped over? No, those are different. There's no way to flip this over and make it match up with this. These two are enantiomers of each other. You would say this is a racemic mixture. Any of that's true here, but those are the products of Br2 with inert solvent. What about Br2 with water? So the difference here is really the first step is the same. You still get a bridge. We still have the bromine up on a bridge. The difference is water attacks that bridge. So here you're going to have the OH on the more substituted side. So on the top where the tertiary position is, we get an OH. Let's say OH on a wedge. That means the bromine from the bridge would be on a dash. And again, those two are anti to each other, so very similar to the previous reaction. And then if the OH is on a wedge, that means methyl's on a dash. That's one option. The other option is, what if we attack from the other face, meaning what if the bridge was on the other face? So if the bridge was on the other face, we could get OH on a dash, Br on a wedge, and then because the OH is on a dash, the methyl is on a wedge. So those are the two options. Again, notice they are anti to each other. That's why we don't have 4 different stereoisomers like we had with HBr peroxides. We only get 2. They have to be where the OH and the bromine, or the bromine and the bromine, like the previous one, were on opposite faces, anti to one another. All right, what about this one? This is a little bit of a trick. Br2 with water, followed by NaOH. Okay, so I'm going to imagine just going back up to what we had right here. Br2 with water gets us this. So I'm going to take one of those products and just draw it again. So literally the first step is the reaction at the top of the page here. So let's say we get Br2 with water, and let's say our OH is on a wedge. I'm going to draw the bond out to the H, and then that means the bromine here is on a dash. And then I get my methyl on a dash. Of course, we have the other option as well, but we'll get back to that in a second. Okay, step 2, NaOH. So NaOH, you could see other bases here at the bottom, like you could see something like sodium hydride, NaH, or NaNH2 even. So those 2 things, 3 things really, they're just really strong bases. So what they do, remember, is we take the H off of this, so you get an O with a negative charge, and then it does an intramolecular SN2 attack. So the O with a negative charge attacks this carbon, taking out the bromine. So in the end, your product is not an alcohol or a halohydrin. You don't have the OH and the bromine. Instead, what you have is an epoxide. So this is one of the ways that we can make an epoxide. Specifically, from the one that I drew, this would be the bonds to oxygen up on a wedge with the methyl on a dash. That's your final product from step 1, followed by step 2 here. And then the other option, if the OH was on the other face, you would get the epoxide, which is the triple triangular oxygen intermediate thing, right? That's what that's called. That could be on the other face. So that would be on a dash. That is your epoxide. So this is kind of a trickier way to make the epoxides. We'll see another way to make an epoxides later, which is generally better for you if you're trying to make these in synthesis. But as like a trick, they'll throw this at you because you're like, what is this? Well, step 1 is an old reaction, right? But step 2 is now making the epoxide. What about NBS and light? So this is a little bit ugly. You could see this written as a little bit of Br2, like trace Br2. If you've seen that, trace just means trace amounts, like a little bit of Br2 and light. The idea here is we want to avoid, if we had just Br2 and light, like a bunch of Br2 and light, it would potentially give us some of this product because Br2 reacting with a double bond could give you this. So to avoid that, we want to have just a little bit of Br2 and light. The light is kind of a hint here that we have some sort of radical reaction going on, radical intermediate. And again, I'm hoping some of these terms like brings back and you're like, oh, maybe not like total PTSD, like, oh God, radicals. But the idea is maybe you can go back and study some of these things if you're like, oh, I don't remember these reactions at all. Good, go back and study them. This is meant to overview all of these products. So this is your allylic halogenation or your allylic bromination. Remember, allylic means 1 carbon away from the double bond, 1 carbon away from the pi bond. So first thing you want to do here is you want to identify any allylic position. In this case, we have 3 allylic positions. Each one of those positions is going to have a radical in this reaction. So I'm going to draw each of those 3 positions here to the side. That's why I said this one is going to get a little bit ugly here, because each one of these could have a radical intermediate. So imagine putting a radical at each of those 3 positions. So here, radical on the primary position. Sure, that is something that's formed in this reaction. Now notice this is not the final product yet, but I'm just showing you the intermediates because this is how you should do it on the test. I have a radical at that position. That's possible as well. And then I've also got a radical at the bottom of my ring. All three of those are formed. The key to this reaction, the reason why this allylic radical is so stable and so likely to form is because this allylic radical can now resonate. So in each of these three cases, we have resonance to consider as well. The resonance would be where the radical comes down here with one electron from the pi bond. That makes another double bond up at the top there. And then your other electron goes to that position. So even if you're not doing a full mechanism, and you might not be doing a full mechanism for every one of these problems, you still need to write this out because if you're trying to do it all in your head, you're going to definitely make a mistake, right? So just be safe here. We're going to pull double bond up at the top, and then my radical goes here. So each one of these three intermediates that I drew can also resonate to give another intermediate. There is a possibility of repeated structures, but again, it's really tough to visualize that in your head. I would draw them out. So this one could resonate, again, electron here, double bond moves up to the top of the ring, and that means the radical is the other carbon that was sharing the pi bond. And then your third option, or really you could say this is your sixth option, is this resonates as well. Your double bond could move to the bottom of the ring, and then you'd end up with a radical at that tertiary position. Notice, after resonance, they're still allylic. That's the whole point of it. Resonance just goes back and forth, but they're still allylic. Each one of these six intermediates could be one of your products if you add a bromine. What we're going to do now is, wherever you had a radical, that's where the bromine could add. Now, I'm not going to draw all six products because we got to move on. We have other stuff to do. But what you want to do is, each one of these intermediates could be where you put a bromine. So your product is not the radical. Your product is putting a bromine at that carbon where you had a radical. So there you go. There's one of your six potential products, and each one of these could give you a different product. There is a possibility of repeated structures here, so just be on the lookout for that, or BOLO, as they say. Does that? So anyway, look out for these things because you could have repeated structures, but until you draw all six of them and look at them, you're not going to be able to do it in your head and say, oh, that's going to give me a repeated structure. Draw them out, see if they're repeated. Otherwise, draw all unique structures. If you were specifically asked for the major product, remember, major means comes from the most stable double bond. So the most stable double bond would be the most substituted double bond, which is actually the first one before any resonance. Of the ones that have all the most stable double bond, then you try to pick the best radical, which would be like a tie between these. That's why asking about major is tricky and a little ugly. But if you are asked about the major product of these reactions with allylic bromination, it is the most stable double bond that gives you the major product, not the most stable radical. Then if there's a tie, you go to the radical stability trend. Okay, so that being said, let's continue on and go to the next page of problems. So these, oxymercuration water followed by H2SO4 and water, these are two very, very similar reactions. Remember, oxymercuration, if you see mercury, think mercury is Markovnikov. So we have a bridge intermediate, kind of like Br2 and Cl2, followed by NaBH4, which is the reduction step to get rid of the mercury. So this is a Markovnikov addition of OH. So we would put the OH at the more stable position on the double bond. Remember, this is just like the HBr reaction where, sure, that's not a that's not a chiral center, rather. If it's not a chiral center, then we don't show wedges and dashes and enantiomers and stereoisomer possibilities. But if you had a methyl down here like we did earlier, sure, that could be a chiral center. H2SO4 and water. And you can see this a lot of different ways, like dilute H2SO4. You could see H2SO4 catalyst with water. You could even see this written as just purely H3O+, as like a shorthand way to just write H2SO4 and water. I wouldn't write those other ways. I would just keep it like this. But if you see the other ways, they're really the same reaction that we have here. So this is also Markovnikov. However, the intermediate is different. This is a carbocation intermediate, whereas here, this was a bridged intermediate. And the difference there is, in some reactions, no difference at all. In some reactions, you wouldn't see a different product at all. In some reactions, you would though. So you're like, oh, well, what's the difference? So this is still going to be Markovnikov. So I'm still going to add the OH to the more substituted side. The difference is if we had the possibility of a better position next door. Here we didn't. Your carbocations formed here. There is no better position next door. But if there was a better position next door, carbocations can shift. Whereas bridges, we don't see bridges shifting. They stay where they are. In some cases, like what we have here, the product is exactly the same. But just keep an eye out because if there's a better position next door, carbocations can shift. Bridges don't. What about BH3THF? So boron, this is one of your anti-Markovnikov reagents. So boron is the anti-Mark addition of an OH and a hydrogen. So here, the tricky part is, so sure, we're going to add the OH to the bottom of the double bond over here. But remember, when we add the OH, this is an anti-Mark addition. It adds OH and it adds an H. We don't normally draw the H, but I'm going to draw the H to show you something here. Let's say the OH adds to a wedge on this bottom of the ring. And we know it's this position because that's the less substituted side. It also adds an H up here on the same face. So if the OH is a wedge, the H is a wedge. But more importantly, because we don't really show the H in most cases, it turns that methyl to a dash. So a lot of people look at this and say, without the H there, oh, isn't that like a anti-addition? No, it's not, because it's syn addition of the OH and the H. So that's one product. The other product would be, what if OH adds from the bottom face? So we get OH on a dash. And again, this time I won't draw the H to show you what you'll probably see more often, especially working backwards. The H would add to a dash here. Okay, fine. But that means the methyl gets added to a wedge. So that's the trick, is that you don't see the H in a lot of cases, right? We maybe ignore that or don't show that. So it makes it look like it's an anti-addition. But remember, it's a syn addition. OH and H added the same face. And it is on the less substituted side, the OHs. Okay, what about our next set of reactions? So OSO4, this one is your diol, your syn diol formation. A diol is a di, so two. OL is alcohol. So you're adding two hydroxyls or two alcohol groups side by side next door carbons, and they must be syn to one another. So osmium is a very strange reaction. It's got those like 4 double bonds coming off of the osmium, the OSO4, but it adds both OHs to the same face. So both OHs, in this case, I'm drawing them both on wedges. If both OHs go to wedges, that means this methyl goes to a dash. That's one option. The other option is, what if you add them both from underneath? If both OHs add to the bottom face, move my hand so you can see what I'm writing in a second. If both OHs add to the bottom, that means the methyl gets pushed up to the top face. So they're both formed. Those are different, so I'm going to include them both. Next, ozone with dimethyl sulfide. So this is one of our fun splitting reactions, right? Where we just split this directly in half. It is really important here that you number. If you don't number, sure, you can still get it right without numbering, but it's more likely that you'll mess it up. So I'm going to number, start at the double bond, go around to the other side of the double bond. That way, when I split this open and unravel the ring, because there's only one connection there keeping that ring together, I'm going to split that open and open it up. I'm still going to have a 6-carbon chain, but now it's opened up, right? So I'm going to keep my numbering 1, 2, 3, 4, 5, 6. And the whole point of this numbering is whatever was attached to that carbon before. So on carbon 1, we had a methyl. So on carbon 1, we'll have a methyl. We had the double bond. That's still there, okay. But now we put an oxygen in its place. So it's an oxidation reaction. We're oxidizing, we're adding bonds to oxygen. And on carbon 6, we didn't see it, but there was a hydrogen there, right? So there's still a hydrogen. And then you get the double bond, which is what we had, and now it becomes double bond to oxygen. So that's the best way to write it. Split it, unravel it, add the double bonds to oxygens. You could get ketones and aldehydes depending on the substitution of the double bond. What about MCPBA? And again, at this point, if you're looking at letters and you're just like, I'm just memorizing this stuff, yeah, I mean, sure, at this point, you might get to that point, but like, hopefully you're not. MCPBA, if I'm going to draw this out just to show you what it looks like, because if you see the formula, it definitely helps to visualize what's going on. So the idea is we have this double bond to oxygen, OOH. So it looks like a carboxylic acid, but it has an extra oxygen in it. So anything of the form RCO3H, so anything with, we call these a peroxy carboxylic acid, CO3H on the end, these all do the same thing. Now there's one more thing that, just to make this more confusing, is we actually have a chlorine on that position of the ring. So it's a very specialized reagent, but anything that has this grouping on it, the RCO3H group, you'll see other things. You'll see sometimes just generically written RCO3H. This makes epoxides. So I know we had another way to make an epoxide earlier, but this is a more efficient way because it goes from a double bond straight to the epoxide, and it's a much better yield without other things happening. So the idea is we get both bonds to the oxygen. The epoxide could be up on a wedge, in which case methyl's on a dash, or the epoxide could be on a dash, so both bonds to oxygen on the bottom face, and then my methyl would be on a wedge. Just keep in mind, MCPBA, I think like M stands for makes epoxides. That's not really what it is. It stands for meta-chloroperoxybenzoic acid, but that's a mouthful, so we just say MCPBA. It must react with a double bond. A lot of people get that confused and say, oh, you got to make an alcohol, then make the epoxide. MCPBA or any peroxy carboxylic acid like this reacts with the double bond directly. Okay, last one here that we have is, what about H2 and platinum? So platinum, palladium, nickel, really any transition metal catalyst. So you could see M as a nice way to just say any metal, but hydrogen plus platinum or palladium, this is a catalytic reduction or hydrogenation. This is the the mechanism of this one. It's really just like a metal surface, like platinum or palladium, and it just grabs the hydrogens. So it just kind of floats around and sticks the two H's on. Imagine they're just stuck on like toothpicks. But the point is, it sticks them onto the same face always. So you would add both H's to the same face. Now, what's a little bit confusing about this is we don't typically draw H's in line angle. So in the end, it just gets rid of the pi bond. That's it. Just gets rid of the pi bond, reduces it all the way down to an alkane, all single bonds. However, one of the ways to make this tricky is you might see it with something like D2 in platinum. D is deuterium. It's just an isotope of hydrogen. So it does everything hydrogen does, except it is specifically not hydrogen, which means you have to draw this in line angle. So if I had deuterium, one of the reasons this is such a popular question with deuterium, or maybe a little curveball here, is you have to draw the deuterium. And remember, this is a syn addition. So the two deuterium atoms, which again, deuterium is just an isotope of hydrogen. We call it heavy hydrogen. It's one of the heavy hydrogen isotopes, along with tritium, which is another one. But the two deuterium atoms both add to the same face. So if both D's add to the wedge, that means the methyl goes to a dash. Or now, because deuterium is not hydrogen, that is a chiral center, as is this one. Those are different atoms. Those are not hydrogens anymore. So you could also add both deuteriums to the bottom face, in which case when you do that, methyl gets pushed up to a wedge. All right, there we go. A lot of reactions we just did. If you have questions, let us know. Otherwise, thanks for watching, and we'll see you next time.